SwayamPrabha. Digital India. Educated India.
In the last class, we had looked at the general expression for the relationship between the advance curve, the type of soil, which is applicable to all the methods, and then we had started with the furrow irrigation systems, and we said that we'll start looking at those relationships which have been built up with the experience of the farmers and through their field trials, the experimental data. These are general purpose relationships which have been introduced with the idea of giving some levels of these parameters, maybe the upper bound, that what will be the recommended lengths of the fields under different conditions of the system. So some of these relationships we'll try to have a look. For example, a relationship between the value of maximum stream size, which should be picked up for a particular condition, and it has been seen that is basically dependent on what is the slope, what is the prevailing slope. So that parameter has been taken into account. This S is the ground slope, that is given in percentage, and Q maximum as the maximum stream size and liters per second. This is a very crude relationship. In fact, if you look at from the point of view that is not having any parameter which is soil dependent. So from that angle, and since you know that the maximum stream size should be basically based on as some parameter which is related with, which is dependent on what type of soil is the prevailing soil. But since it's a very approximate relationship which is only giving an indicative value, that what is the range, you shouldn't be very much off the range. So looking into the ground slope, you can pick up a value of stream size which is reasonable. For example, using this relationship, you might get that for a slope of 0.1, you are getting a maximum stream size of 6 liters per second. 0.5 will give you 1.2 liters per second. Similarly, a slope of 2% will give you a stream size of 0.3 liters per second. Now comes the other conditions. For example, in the case of furrows, you don't go up to the slope of 2%. The 2% slope can be very erosive slope under some conditions. So along with these relationships are not to be used in isolation. These are only giving you some order of magnitudes which have to be used very judiciously, and you can make use of these relationships if you are aware of the other constraints. The maximum slope, let's look at some of the furrow grades which are normally the recommended grades. These slopes again, they have come out, they have been suggested with respect to the trials, field trials, as well as the experience of the farmers. There are many factors which will influence these suggested furrow grades. If we start from the beginning, when you are trying to bring some area under irrigation, when you are trying to lay the fields, it will be basically a function of what is the prevailing slope. So the natural slope which is prevailing in the area, that will be the major constraint or major condition which will decide what is the grade to be adopted. In many situations, you will find that if the natural slopes are excessive, if you go in for the formation of those areas or the grading of those areas, you might turn the soil upside down. The soil which is fertile soil might be taken away and replaced with the soil which is exposed soil, which has come from the lower layers. That soil is not very fertile. So you will try to avoid that situation where the exposure of the soil might be a possibility if the grades are very excessive. Similarly, the grades which are generally adopted in furrows, they shouldn't be more than 1.0%. This is the maximum limit, though it can be exceeded depending on the soil type, what type of soil is in question. If the erosion is not a problem, if the furrows are cultivated furrows, the erosion will be again lesser. So you can, but there is the general limit which is applicable to most of the soils, that one shouldn't cross these limits. Similarly, from the point of view of some of the conditions which can be prevailing conditions, you might find that the minimum grade, there is the maximum grade, the minimum grade should not be less than 0.1%. Because if it is less than 0.1%, then it will be a flat area. You might find problem in moving the water in the furrow. So from that consideration, the minimum grade as the limitation, that if the grade is, there should be some grade so that the water can move in the forward direction. Similarly, in the case of changing conditions, as we were discussing in during the last class, that if you have conditions varying from arid areas to semi-arid areas or to humid areas, you will find that the slopes will be, the grades will be also affected from those considerations. So in arid areas, let's look at some of these. If you have arid areas, the rain is, as naturally will be very small in these areas. You might be able to go up to slopes of around 3%. Again, the soil will be a constraint, what type of soil you are using, but you might be able to achieve such a slope also, provided your stream sizes are very small. And those are the other conditions. If your stream sizes will be small, then it will have its own repercussions. The repercussions can be that your length of the furrow might be reduced drastically because of the fact that there will be a lot of infiltration taking place in the upstream end of the furrow. So all those conditions will be the other conditions which will govern what slope can be achieved, what streams, when it has to be looked at along with the other parameters of stream size, of the soil type. The humid areas on the other extreme, you might find that the slopes may be as low as 0.5%. So they shouldn't be, this will be the limiting slope, that you should try to avoid the slopes more than 0.5%. At the same time, you will like to give some minimum grade so that you can have the water which gets accumulated in these humid areas. It should be, these slopes should be able to drain off that water quite comfortably. So the minimum slopes might not be less than 0.05%. Now this becomes the range, which is only a recommendation. The actual slopes, if you want to find out, you will have to go in for the actual designs, where you will have to look at the other parameters in combination with these parameters and suggest or select those parameters accordingly. That is what the design is all about. That you have to ensure that the efficiencies are proper. The efficiencies will be proper if the wastage is less, and then the erosion is avoided, the sedimentation is avoided. All those things have to be taken care of. Similarly, along with these slopes or the grades, the field sizes is another important parameter which must be considered. And there are suggested field sizes which are available in literature on the basis of the field trials as well as on the basis of the experience of the local areas. And in general, you will find that if you increase the field length, in the case of furrow irrigation, it will be the furrow length, because field is composed of many parallel furrows. By increasing the field length, what it results in is increase in the FAR. And FAR we had defined as a ratio of advance time to the net time. You will also, if you just look at the various relationships we have derived so far, if you increase the FAR, what it amounts to? If the FAR is more, there will be more of deep percolation. That is what we have seen earlier in the previous lecture, that when the FAR increases, I had given you a table also. If the FAR increases, what happens? Basically your advance time is increasing. That means the length, the higher the length of the field, the larger the length, your TT will be larger. The TN may or may, there is something which is the requirement. So for a larger TT, FAR will be larger. If the FAR is larger, the disparity of infiltration will be much higher, and you will have more of deep infiltration, or the percolation loss will be more. So this increases percolation loss, and which in turn will result in reduced efficiency. From these type of relationships which have been put forward, ultimately you will find that you have been given recommendations in different forms. One form of recommendation is maybe in the form of a relationship or a table which is giving you for different slopes. For different slopes, and for different average depth of application. Now the application, the irrigation application requirement is not a fixed requirement. It might be different, it might be varying. It is something which is dependent on the management and the farmer, at what time they want to irrigate, and accordingly the amount of water which has to be applied as irrigation water. The depth can vary. It also is a function of different types of schemes, whether it is a rotational irrigation scheme or the on-demand irrigation scheme. We'll look at those things later. But it's true that the depths of applications can vary. So for different depths, you might find that there are different relationships, and these depths are also dependent on what type of soils are the prevailing soils. You might have clays, you might have loamy soils or sandy soils. So under each of these soils, the actual depth of irrigation, I am just taking some representative values, or the values which are normally used as depths. These are the depths in centimeters. All these are in centimeters: 7.5 centimeters, 15 centimeters. And so on. These are the possible, these are the normal depths which are used in irrigation. So the suggestions or the suggested parameters can be of this type, that for a specific slope under different conditions of soil for different depths of applications what will be the recommended length of the furrow. So this is giving a recommended length of furrow in meters. I am just picking up some of the values just to show you that how much variation can be there from one type of soil to another type of soil and from one slope to another slope. Then let us have a look at these two more values for a slope of 0.5. If you want you can see the variation. When you have for an increased slope, you could get for the same type of soil and for the similar depths, you could use the longer lengths of the furrows. But when it became more steep, for example, for 2% slope, if we look at the recommended maximum lengths, these are basically, let me put here, these are the maximum lengths. So your length should be preferably below these lengths. There will be many other constraints which might force you to reduce the lengths than these lengths. These are just the recommended maximum lengths which can be used under some of these conditions. Now you see here that when the slope has increased and the grade has increased, the lengths are again reduced. In all the cases is the same. I just picked up three slopes. In the beginning, the slope was 0.05. The lengths were more for the clay soils, less than that for the loamy soils, and even lesser for the sandy soils, which is quite understandable because of the variable infiltration rates. Under these, the infiltrations rates are maximum under sandy soils, so you cannot afford to have very longer lengths. Otherwise, you will have a lot of the deep percolation losses. But when the slope increased to 0.5%, for the same soils, the lengths, the possible lengths which you can adopt, they are much higher lengths. But the trend is same. When you go from clay to loam to sand, again for those slopes, you cannot your lengths are reducing in order of magnitude. Within the same soil, if you see here from 0.05 to 0.5 to 2%, it increased first and again it reduced. Now this reduction is on account of the erosion problems. Okay. The erosion plus also the velocities which are the movement, the rate at which the water is moving, it might have problems of erosion, plus the accumulation of water, the surface runoff also can be another problem, which can be very detrimental in terms of losses, because those surface runoff is again a form of loss. The water is just getting passed over the furrow, is not getting infiltrated into the soil, then is of no use. Is basically is again a loss. So whether is the loss because of deep percolation or whether because of surface runoff, it is a loss. So these recommendations are on the basis of those evaluations, that so that your efficiencies can be maximum under these prevailing conditions. So if you are starting with a design, these recommended values can be taken as the starting values. These can be taken as, treated as the first assumptions of the design parameters. That is what these recommended values should be used for. So once you have these starting values, or if the data is not available, you cannot do anything. You might have to do your designs approximately on the basis of these. You select the parameters and look at the combination of various parameters and select a value which is a reasonable value, and even you can find out under various conditions what will be the efficiencies which you are producing. Either you can go in for the evaluation of those some segments of the furrows, the actual test runs, and find out what will be the efficiencies, and then on the basis of those efficiencies select a set of parameters which give you the best efficiencies, or you go in for the better relationships provided you have the data and as well as the computational facilities, or even in some cases the other related data which is required for these computations, which are based on better relationships, which are closer to hydraulic relationships. So let's have a look at some of these relationships which are based on hydraulic relationships. And these hydraulic relationships which are used for design purpose of furrow irrigation design, they are not again exact relationships, because there is no need, you don't justify using the exact relationships of hydraulic flows in these areas because of the three major reasons. One is that the lack of required data, you require quite a good amount of data. Even that can be taken care of. I mean, if the data requirement is there, if you are going to get the best results, no problem, you can get the data, you can afford to spend money on collection of the data. But it's not that only, that is one aspect only. The other is that even if you go in for the data collection, still there is a lot of spatial variability in all those parameters which are the parameters which are influencing these processes. So the spatial variability of the involved variables For example, even if you take the infiltration properties of the soil in a particular field, you are not certain that how much that those properties are changing from that point where we have done the infiltration analysis using the infiltrometer maybe. That is only a point in the field. If you go from that point to another point, your infiltration characteristics are going to be different. Similarly, the properties like the roughness coefficient is changing from point to point. The soil might not be truly uniform. So is not worthwhile using very exact relationships if your data is known to have spatial variation. Okay. So many of the relationships which have been put forward, they are they are approximate relationships based on the hydraulic relationships to start with, but using a lot of assumptions on the way, and they have ultimately been transformed into more empirical relationships. You cannot say that they are based on the hydraulic relationships, but with a lot of assumptions, wherever the assumptions were needed, they have been incorporated, and they don't remain to be as exact as you will like to be, or when you use them in the experimental setups in the laboratory conditions. That is not justifiable. So most of these relationships which we are going to look at, they are the approximate relationships, and most of these have been put forward by the soil conservation services of USDA, US Department of Agriculture. Then there are some other peculiar problems with the furrow irrigation. We have formulated some equations for for infiltration process, but they have to be revised. Why? Because in the case of furrow, if this is one segment of the cross section of furrow, you have this is your water level in the furrow. In this case, the infiltration is taking place along this perimeter. So the major difference is that the infiltration is taking place on perimeter of the furrow, and for all practical purposes you want to represent this as in the form of depth over the area. So it will be much better if we can find some equivalent depth over surface area of the field. So we will have to do some transformation to our equations so that we can convert this into equivalent depth. One possibility is that we just assume that this curvature can be flattened, and then you find out and that is what is done basically in this particular case. You try to make the corrections to the existing equations, so that you can incorporate this particular fact of having the furrows which are infiltrating water along the perimeter of the furrow.
So this vertical infiltration and the lateral infiltration, those values may be different or same?
As the question is a good question, that the infiltration now in this case, the question is that whether the infiltration which is in this particular case, in the case of furrow irrigation, is not only vertical, is lateral also. So whether the two will be same or not. Yes, they won't be same, there will be some difference in the infiltration, but we are approximating them to be, what we are assuming is that if this perimeter, if we try to unfold this furrow, how much will be the depth accumulated over this length of the perimeter. Okay, so it will involve some assumption, maybe that it is giving you a value which is slightly less than what is actually happening. There will be more infiltration in actual practice because of the lateral dryness of the adjoining parts of the soil, but that is what is done in the actual practice. If you want to take care of those the additional infiltration which is taking place, you might have to improve upon those figures still to an extent, but that is taken care of by taking the spacing between the furrows to an extent. What we are doing is that we are saying we are having an area which is having furrows, and we have laid down the furrows at a known interval. The spacing between the furrows is known. So if the spacing is more, there will be less water area which is wetted. If the spacing is less, the wetted area is much more. But when you try to use the perimeter, you are in any case you are increasing the length of the area. So that is indirectly taken care of there when you are unfolding this. Now, the intake rates of the furrows, there is a slight difference in measurement of these intake rates. In the case of other irrigations, the border irrigation as well as the level irrigation, what you are doing is that you are taking the infiltration rates through the infiltrometer test. Whereas in this particular case, it is not possible to use the infiltrometer test because of the fact that is not the vertical infiltration. So what we do is that we do the inflow outflow analysis in a segment of the furrow. So you take a representative segment of the furrow. If we let's say that this is a furrow in plan, and I take a segment. This is my upstream location of the segment, a downstream location of the segment. So I install some device at these two stations which will give me the measurement of I can observe how much is the inflow and how much is the outflow from this end. So you can even install two partial flumes. Any device which you feel, normally the partial flumes are used in these furrows. So if I know the inflow and the outflow, I can find out how much is the amount of water which has infiltrated into this segment, and that gives me the intake rates. So to find out the intake rate, I use such a measurement. Let's say that if y is the intake rate, you can express it as length into P into where Y is nothing but the equivalent depth of infiltration, okay. This is the equivalent depth of infiltration over the wetted surface area of the field, and this is in millimeters. L is the length of the furrow segment considered. In meters. P is the adjusted wetted perimeter. And this is again in meters. Then we have V in is the volume of inflow. This is absorbed in liters. Similarly, V out is outflow volume, again in liters, and Vs is the volume of water in storage. So there might be some volume of water which is at that particular time when you are taking the measurement, there will be in storage between these two sections. So this is basically an inflow-outflow analysis, and the average value of infiltration, if you start the analysis at a particular time and take the final value after a very long time, then what you are getting is average value over this period. So to find out the variation of the infiltration over this segment, you will have to take some intermediate observations. So you keep on taking the observations at some interval so that you can find out how this infiltration was varying over time. Okay. Now in this we have used two terms. The inflow volume, no problem, you can measure. The outflow volume you can measure. Length is known. There are only two items. If you look at this equation again, the adjusted wetted perimeter, which will be difficult to find, and Vs, which is the volume of storage, the water in storage between this section. There have been relationships which have been formulated for these two items so that they can be used comfortably, or they can be evaluated without any problem within the known quantities which are easily observable. Let's look at the first, the adjusted wetted perimeter. P is given as this expression. Is basically obtained from the Manning's formula. You can see the various most of these relationships have been derived from the Manning's formula. Now this is the expression which has been found to give you the adjusted wetted perimeter. And the various terms you already know. Q is the volumetric inflow in liters per second. So Q is in liters per second. N is the Manning's roughness coefficient, and normally the value of N is in general taken as 0.04, and S is the furrow slope, basically is the hydraulic gradient, but is assumed to be equal to the furrow slope, and this is given as meters per meter. And the channel storage, or the volume of water in storage, which we have just mentioned, Vs, the expression used for expressing Vs is so in this expression also all the quantities which have been expressed, they are the same as before. And length here is there's the length of the furrow segment which is considered, that's in meters. Now you remember the infiltration equation which we have earlier written in terms of time and these different parameters A, B and C. This equation for the case of furrow irrigation design is modified to incorporate the wetted perimeter This is the wetted perimeter. And W is the furrow spacing. In meters. Now you can see that the impact of having a very large furrow spacing will be that your this Y will be reduced considerably. So that is how the impact of having furrows with at different spacing, or even if the space is small, still the Y will be much comparatively lesser than if you are using this expression or the same equation on a border irrigation, on a border or on a level basin. Okay. Then let's look at some other expressions which we are going to use. One is for the advance time. The advance time can also be computed on the basis of this equation. This is the expression which is derived to express the advance time, and the various quantities which are used here. TT we know that is the advance time in minutes. X is the distance down the furrow. That means from the upstream end of the furrow, what is the distance we are considering in the direction of the downstream length of the furrow, and the longitudinal direction of the furrow, and this is in meters. Then F and G are the advance coefficients. And Q and S we have already seen, they are the same parameters. Q is the volumetric inflow rate in terms of liters per second, and S is the flow, the furrow grade, or is the representative value of the hydraulic gradient. There is these parameters, these coefficients F and G, they are available for different family curves along with the parameters A, B and C. So these are the coefficients which are available in literature. They are the fixed values for different family curves. I will provide the table of these coefficients. These are basically to give you some order of magnitudes for different family curves, the intake family. Now, these intake family curves have been designed, or they have been defined by the SCS, the Soil Conservation Service. We have discussed that earlier, and they have evaluated these curves for these coefficients along with F and G coefficients. For example, I will give you one or two values which will give you some idea about the order of magnitude of these. This is the value of A when the intake family curve is 0.05, and this we had discussed earlier also, that the intake family curve of 0.05, it means that this is a relationship, this is the equation for which these parameters are applicable for a soil type whose basic infiltration rate stabilizes at 0.05 inches per hour. Is it inches per hour? I am not we'll have to check that, I am not sure, but this gives the stabilized rate, and that number they have adopted as the number associated to the intake family, the intake curve, and that the set of those curves they are calling intake family. Okay. So this indirectly it designates what type of soil you are using, and all those characteristics of the soils are given in the form of the intake family curve characteristics. The value of B is 0.618, C is taken to be constant. C is basically introduced to change the shape of the curve. In some cases, if the soil characteristics are such that you are not able to represent the soil through a single parameter, then you might be able to change the C and get if there are two curvatures of the soil, the infiltration capacity curve, then this C parameter is helpful, but in this particular case all the family curves are having the same C value. The F value is 7.16 for this intake family, and the G value is 1.088 into 10 to the power minus 4. Now this is given for the different types of soils, and the number goes up to 2, for which the parameters are again given. This table will be made available to you, and this is quite a useful table. I think with that we'll stop today. If there are any questions, I'll be glad to answer those. Thank you then.